everyone. I hope your test 2 went well. We're starting a new section today. It's on regression lines. I've got here a list of the things. Got a list of the things that we'll be covering in that section. We're going to be talking about a number. It's called the correlation coefficient R. I'll be doing some notes on that. Very, very closely related to it, there's another number called the coefficient of determination. In most textbooks, it's called R squared, but you might see it called capital D. I prefer R squared myself. I think that's what this textbook calls it, so that's good. We've seen regression lines. We're just going to talk a little bit more about them and using them. We're going to look at, and we've done this, how to calculate residuals. This is new. We're going to look at the effect of outliers on regression lines. And then we're going to finish with some common mistakes. And we have done some of these, but not all of the mistakes that people make, people meaning politicians when they want to lie to you, or companies where they want to give some data and put a kind of good light on it, how they can tell you something which may not, strictly speaking, be numerically wrong, but is kind of wrong in the sense that it's not telling you the whole truth. So we'll be looking at how people do that, or how we make mistakes, because sometimes they're just natural mistakes. There's no malice involved. They've just used the regression lines in a way that they weren't designed to be. So start with my first one. These correlation coefficients. Now, correlation coefficient is a number, and it's going to be a number between 1 and -1. It's never bigger than 1. It can never be less than -1. If you get a correlation coefficient equal to 1, which is highly unlikely, but I guess you could get it, your data is a perfect positive straight line. You couldn't get better than that. The x-axis is your explanatory variable. Let's put that term in again. Can anybody remember what the y-axis is called? It has a name.
That's the response one, isn't it?
Yes, it is. Now, what the correlation coefficient R does is it measures how good the data is to a straight line. So the closer it is to being 1, the closer it is to being that. So can you imagine you had a set of data where the correlation coefficient was 0.9. It wouldn't be a perfect straight line, but wouldn't it be a darn good straight line, right? It'd be very close to being it. So you might get data that looks something like this. And that could be 0.9. So we are not going to use words like strong, moderate, and weak, or moderately strong or moderately weak. Weren't they very vague descriptions of how good the data was to be in a straight line? What instead you can do is you can use a number called the correlation coefficient. So would you agree that that's a very strong fit, right? That's a good strong fit. Now, you could get something like 0.5. And if the data was 0.5, yes, it would be linear, but would you agree that It's very weak. And if you got an R value, a correlation coefficient value of 0, you would be looking at no discernible shape. You know, like the shotgun on a target, right? Somebody got one of those shotguns and blasted, and when you just get a big circle of nothingness. So we don't talk now so much about, oh, this is a strong fit or a moderate fit. What we would say is that this has a correlation coefficient of 0.5 or 0.9. Now, these numbers are actually calculated, right? They're not just made up numbers to try and, you know, put a value on how strong something is. They are calculated from the data. And the formula for calculating them is extremely difficult to do by hand. And I don't know of anybody who actually would do it by hand. So if you ever need to do it, it's going to be done by software, right? Salt will just tell you what it is, or the question in the homework will tell you what it is. Have you noticed that all three of these have positive slopes? When the correlation is positive, not only do you know how good a fit it is, but you also know that it's positive slope. Now, in the same vein, you could get these three situations. I'll try and do these pretty quick. Can you imagine the data being a perfect straight line but pointing down the way? Right? I'll mute that. There we go. So can you imagine the data being a perfect straight line down the way? What do you think the correlation coefficient for data that was that nice a fit?
-1.
-1. And if it was pretty good, or really strong but not perfect, just be a little bit different with this one, you could get -0.81. Agreed? Pretty strong, pointing down the way. If you get a bit weaker, you could have the sausage pointing down the way. And that could be -0.6. And of course, this is really only for completeness sake, because I've already done it. When a correlation coefficient is 0, doesn't that mean there is no direction to the data line, right? In fact, another way of looking at it is, couldn't I draw any line I like and it would be just as good or bad as any other line? Could I say, oh, well, the data's that line, the data's that line, or the data's that line, right? Wouldn't there be no particular, one is clearly a better direction than any of the others. And that's essentially what the correlation coefficient does. Now, there are a couple of types of questions that you would get on this. So let's look at what some of them might be. Right, here are 5 numbers that might, whoa, that's not good, whoever that was. So let's do that. A word of advice: when you join class, go on mute. There. Phew. God, that hurt my ear, that one. Right, where were we? Right, so here's a kind of question you could get. Here are 5 numbers. Which of these numbers could be a correlation coefficient? Right. Could 0 be a correlation coefficient? Yeah. Could 0.3 be one? How about -0.8? Could that be a... No. Why? It's too big. Isn't the biggest value of R 1? Could 0.99 be a correlation coefficient? Yeah. So you might get questions, if I'm looking at one right now, which gives you a set of numbers and it says to you, which of the following numbers, oh, they phrased it the other way. Which of the following numbers could not be? In which case, wouldn't that be your answer, that one? Here's a different question. There are 4 sets of data. Here are the correlation coefficients for these 4 sets of data. Which one of them, I'll call them A, B, C, and D. Which one of these has the strongest linear relationship?
The 0.7.
Yes, it would be that one. Why? It's the biggest R. Now you might say, but it's a negative number, which it is, but don't you not really care about plus or minus? Isn't it how close to being 1 is an indication of how strong the data is, right? So this one is the strongest. Which one of the 3 that's left is the weakest?
The 0.1.
Why? You're right.
It's the closest to 0.
You're right. So if I gave you only the correlation coefficients, couldn't you tell by looking at just those numbers, right, these guys here, which one would be the best fit to being a straight line, right, the most accurate, and which would be the least accurate? In fact, can't you put them in order if somebody asked you to? Now here's a different kind of question that you can be asked. This one is involves pictures, if I can find one. Yeah, okay. I'll switch over to it and we'll show you them. Now you don't need to do any real numbers with these, but here is 4 sets of data. Which one of those has the strongest relationship? Graph 1, 2, 3, or 4. Strongest relationship.
2.
I'd agree. And here's, I don't think they asked this question, but I'm going to. Which one of these graphs has definitely got a positive R value? See, 1. I agree.
1.
Yeah, 1. Now, when you look at 3 and 4, would you agree that they are not very straight line, not very linear? 4 is not very linear because it looks like a shotgun blob, and 3 is not very linear because it looks a bit like rectangles, doesn't it? So would you agree that both of them have very weak R values, very close to 0? Right? Any guesses about which one of those 2 is likely to be the closest to 0?
Is it 4?
I see a couple on 4. My gut feeling is 4. And I hope I'm right, but it's very hard to tell. The reason I think this one fails is because isn't it more long than it is tall? I know that's not very much, but isn't it wider than it is tall? And I think that's enough to make a difference. Now, if this was a perfect square of data, can you imagine it was 4 rows of 4? In a way, wouldn't that be the ultimate version of no direction? And no direction is R equals 0. So it might win in that case, because this set of data here, it could be a little bit more up than it is down. You know, that's all it would take to make this one 0.01 and this one 0, right? You know, there could be that little difference. So that was good. Oh. Here are the same 4 graphs, but graph 1 has got 4 numbers it could be, and you have to pick only from this choice of 4 which one you think graph 1 is.
I'd say it's 0.6.
I would think that that would be correct. I think it's a no-brainer for the next question. Suppose it was graph 2 that we're talking about. Which one of those 4 numbers is graph 2 going to be? I think this one's very easy.
Negative 0.9.
Would you agree it's the only negative one in the list? So it must be that one, right? The other 2 choices have got me a little bit flummoxed. One of them's a 0 and one of them's a 0.3. My gut feeling is that that there should be the 0 and that there should be the 0.3. But I just think that they've made a mistake and they've meant to put a 4th line in there. And only because I think they've done that, even though they didn't, that one's going to be 0 and that one's going to be 0.3. Now, although that's a mess, right, it can still be 0.3. Any correlation coefficient that's under 0.4, when you look at it, just looks like a blob, right? So you have to be like bigger than 0.4 or, you know, less than negative 0.4 before you even see a sausage appear. Right? So they're very weak. Data can still have an R value of 0.3, and you might not even see a linear when you look at it. But, you know, when you analyze it, I guess if you looked at it with a microscope, you might begin to see a little bit of direction to the data. Let's move on then. This picture. There is a guy called the coefficient of determination. And who is he? Well, the coefficient of determination, called R squared, is essentially just a different way of measuring the same information, but it does it in a different way. The R squared is a big clue to what you do. So if R is 1, R squared is 1, but you normally don't write R squared as a decimal. It's normally converted into a percentage. So R squared would be 100% fit. In other words, 100% of the data fits a straight line. Now, if the R value is 0.9, R squared is 0.9 times 0.9, which is 0.81, but we call that an R squared of 81%. Are you comfortable that they use percentages for R squared, but decimals for R? And you're also comfortable at how you calculate? What would the R squared for this set of data, which is an R value of 0.5, be?
It's like 25%, isn't it?
Yeah, 25%. And of course, 0%. Now, they have a fancy sentence, which I guess I should write down probably in red. When they talk about R squared, the coefficient of determination, they say something like this: the percentage of the model explained by the data. It's not a very good sentence, but you'll see it written in textbooks, you know, if you look up the dictionary version of what that is. And it's a percentage of the model explained by the data. I think of it as like this. If R squared is 81%, 81%, and I forgot my word, it's the percentage of the variation in the model that is explained by the data. So back to this one. If I see an 81%, I just think of it as 81% of that data is going to be darn close to being the straight line. And if I see a 50% or a 20%, 20% of the data is going to be near the straight line, but doesn't that also mean 80% of the data is miles away, or it could be miles away? And that's just my way. Now, when you look at negative R values, the R squared here is still positive 100%. And this one here, well, I need a calculator for this one. If you take negative 0.81 and you multiply it by negative 0.81, you get a positive R squared of 65.61%. And this one, you get a positive value of 36%. And of course, this one, you get 0 again, so it's 0%. Have you noticed that the R squared, because it is positive, is the same number whether the line points up or down? It's a positive number. So when we talk about the correlation coefficient, so the coefficient of determination, which is number 2. It always has an R value between 0% and 100%. Does that make sense? The best you could ever get for an R squared would be 100%, but a perfect fit. And the worst case scenario would be 0%. So far, so good. So you could get questions where they give you a picture. Well, let's do that. One of the data looks like this. Data's and it looks like this. Now, one of the data looks like that. And which one of those pictures, which one of those data sets is the one that's most likely to have an R squared of 80%?
The top left one.
Agreed. Do we care that the data is pointing down the way? No, R squared doesn't care. Would you agree then that maybe my drawing's not as good as it could be? Would you agree that is, out of the 3, that's the most likely to be the 75? And although that looks, and I'm sure it does to everybody, although that looks like a 0, couldn't it be a 10% or a 20%? Because once you get to that range, they all look like blobs of nothingness. You can't really look at it and distinguish between one blob and another blob. Right? One could be 5%, the other could be 10, and you wouldn't be able to distinguish between them. So if you were given a picture, do you feel comfortable if they gave you a list of R squared that you could choose from a list which one works? So that's the kind of question you get. Then you get a question that might look something like this. There's a data set, and I'm telling you that R squared is 91%, and I'm asking you to find out what the correlation coefficient R is. Now, you've got to be careful how you do this. Would you agree that there's probably going to be a square root happening somewhere? Problem is that people make a mistake about which one to do. Don't do this one. Let's do it and kind of show you why that doesn't work. If you do the square root of 91, you get an R value of 9.5. Doesn't that not make sense? Would you agree that R values have to be between 1 and -1? So forget it, right? What you do, so do this instead, is find the square root of 0.91. Does that make sense? That why you would use 0.91, even although the R squared was 91%. And the reason for that is, isn't 91% just another way of writing a decimal? 0.91. So the square root of 0.91 rounded off is about 0.95. So the correct answer to this one was 0.95. Suppose we this there, and I tell you that the R squared was 49%. Then to get R, you take the square root of 0.49, and I picked that one because it's a nice number. But the answer isn't 0.7, is it? There's a little bit extra to get the final correct answer. What is the R value for this data?
Minus 0.7.
Right. Do you notice that you have to take into account the picture? Is it sloping up? Positive R value. Is it sloping down? Negative point R value. So if someone gave you this question, and asked you to find R, there's actually two possible choices, aren't there? And I've just done that darn thing again. And my brain keeps doing that because I know I need a decimal. And so I keep writing it as a decimal, right? So R squared is 36%, and they ask you to find R. Now, you would find the square root of that 0.36. But here's the mistake. That isn't the only answer. If there is no other information given to you, isn't there two possible answers for a data set that has an R squared of 36%? Couldn't it be the straight line pointing up the way, positive? It might equally be the one pointing down the way. So unless they gave you some other information to decide between the two, technically, isn't there two answers that could be possible? Any questions about that? Do you feel comfortable? Okay, let's see if I can find something here. Okay, I'll just write this question down. It saves me jumping back and forward. This is a version of question 12. It says the correlation between height and weight is R equals 0.6. Question A says, calculate R squared. So that's the first kind of question. That's the easy direction. Don't you just take nothing 0.6, square it, which is 0.36, and then write down 36% or 0.36. Depends what the book says, but unless they say otherwise, always go percentage. Let's see if I can find one the other way around. This is a version question 14, where you are told that R squared is 61%. And they give you a big table. Now, this is not the table, but I'm going to kind of pretend it is. And you are told latitude and temperature. And it goes something like this. 26 gets you 83. 34 gets you 75. 35 gets you 71. And 40 gets you 62, right? Now that table is going to become important at the end. You're being asked to find R. Well, it's going to be the square root of 0.61. And the square root of 0.61 ends up being approximately 0.781. Now we know from these questions, isn't it a plus or a minus? And this time, it's not a picture. I think when they give you pictures, isn't it easy? Oh, it looks like that, it must be positive. It looks like that, it must be negative. Instead, they've made it a little bit trickier. Here is the table that this data was created from. Positive or negative?
Negative,
Agreed. Why, Mark?
because as the latitude goes up, the temperature goes down.
Okay, do you see that, guys? As the first guy gets bigger, the second guy gets smaller, right? As the explanatory variable, the x gets larger, the response variable gets smaller. When you have that, you are having data that goes down the way, and that's how you tell it's negative. Now, you can imagine in the homework question, wouldn't there be two choices and you put the first one, it doesn't work, and then you put the other one and it does work. But that's not very good for online tests, because online tests don't tell you you're wrong, right? So you really do need to be able to tell the difference. Are we good so far about the connection between R and R squared, and how, if you tell me one, I can find the other? These questions up here, aren't they just baby, is it this one here? No. This question here we go. They're just baby questions, aren't they? If you tell me that number, I square it and make it a percentage, right? You don't need to think too much. This can be trickier, isn't it? Because the decision's going to be plus or minus. That should be the hardest part of your decision. Are we comfortable with those two topics, 1 and 2? Good to move on. Okay. Now, this guy we have met before, but we're going to do some more of him. This is topic 3, equation of a regression. Now, calculating the equation of a regression line is notoriously difficult, so nobody would expect you to do it by hand. So you're either going to use solve or you'll be told the thing. So let me make up one where the explanatory variable, the x, was hours in study that a student had before an exam. And the vertical, right, the response variable, was the grade that the person got, right? And since I'm trying to make people study, I will give you that data. Now, isn't this data saying the more hours that you study, the better their grade tends to be? So you collected students and said, okay, be honest with us. How much did you do last week or the last couple of days studying for this exam? And someone will say, I did 1 hour. Some says I did 12 hours, whatever. And the grades are a reflection of that. Now, you would have an equation. If you were doing it in mathematics, the equation might look something like this. Y equals 5x plus 30. Let's just say that as an example. We would call it y hat, and that's predicted y, but we wouldn't even typically, although sometimes they do, use x's and y's. We would say predicted, oh, I'm going to have to give my name for that response. So hours of study and scoring a test. So you would say the predicted score that you got in a test would be 5 times the hours of study plus 30, right? So you would typically write the equation a little bit less mathematical and a little bit more like a formula, right? And this equation, this 5x plus 30, would basically be that line. Right. Now, from your algebra that you've done, isn't 5 the slope and 30 the y-intercept? So this point here would be 30, wouldn't it? The y-intercept. And wouldn't the slope be, if you went along 1, you'd got 5? Okay. So far, so good. So we're going to look at these equations of regression lines, and we're going to use them to do some basic predictions, and we're going to look at these two numbers in more detail. So let's get the first one. There's a student who did 10 hours of study, so a lot of study. And what was that student? The question would be, what was the predicted score that such a student would get? So the predicted score would be 5 times the hours that they studied plus 30 points. So that would be 5 times 10 plus 30. And we would predict that the student got 80. The test is probably out of 100, right? So we'd say that student, we make a prediction that that student got 80 out of 100. Now, it's a prediction. It doesn't mean I guarantee I'll sell my house that that student definitely got 80. Because in real life, couldn't that student have got 85 or 75? But as a predictor, it's probably going to be close to 80. And if you got like 15 students that all studied 10 hours, wouldn't the average probably come out as 80, right? So it's a number that is a kind of typical value for that number of study, right? So don't make it like it's telling you what's definitely going to happen. Think of this formula as it's telling you what's most likely to happen, right? Some run about 80. Right? Now, you could be given an extra question with that, so I'm going to add this in, and it's called the residual. The residual is essentially the error. So let's suppose that this student who studied for 10 hours, we predicted they got 80. But his real score was 82, right? A pretty good predictor, would you agree? It didn't quite make it, but it was good enough. And the residual, the error, is found by taking the real data and subtracting what the predicted answer was. Well, in this case, they really did get 82, and we predicted 80. And so 2 would be the residual. Are you comfortable about how you would calculate residuals if someone told you what the real score for that particular one student was? What else could we do? Suppose we had a student Now, this question's kind of back to front. Suppose there was a student who got a score of 90 in this test. We need to predict how many hours did he study for. Right, now we can use the equation, right? This guy up here. to even answer these. And when we do it, doesn't it become more like a solving an equation in math? I'm going to use this form, but some people find this form easier because it looks more algebraic, right? If you don't like all the words, just write it as y hat equals, in this case, 5x plus 30, and then solve for that. So what do I have? I have the predicted score is 5 times the number of hours studied plus 30. If you tell me that that student scored 90, then aren't we trying to solve that equation? Okay. Think of algebra. What would we do to both sides to solve this equation? What would be the first thing I would do to both sides to try and solve this equation?
Subtract 30.
Okay, so if you subtract 30 from both sides, it now looks like this. What would I do to both sides now to find out the number of hours that that person studied?
Divide by 5.
And so the answer we got would be, we would be saying 12 hours is what we think that student probably studied for. Did that mean that this particular student definitely studied for exactly 12 hours? No, it's not like a math equation. X definitely is equal to 12. You know, in math, when we tell you something, it's a kind of certainty thing, right? That is the answer, right? It's not wiggle room, it's 12. But in statistics, isn't the answers always kind of qualified by, this is the best prediction of the answer, right? We think it's 12 hours, it probably will be darn close to it, but you know, it might be 11, right? In real life, for that particular student at least. Any questions about that? Are we good? So let's look at this formula in a different way. Actually, I want to keep this picture. So we have the predicted score is 5 times the hours that they studied plus 30, and also written as this guy. There are two numbers here. This 5 is called the slope, and this guy is called the y-intercept. You comfortable about those names? You've seen them before for straight lines, same name in regression. These two numbers very often tell us a little bit about the process that we're trying to see here. What do I mean by that? Well, for every one extra value of x, the y value increases by 5. Wouldn't you say that's a very long-winded way of saying the slope of 5, right? For every one x, right? For every one that you add onto the x, won't the y's increase by 5, right? Now, if I turn this x and y into the context here, this would be for every extra hour that a student studies, his score in the test will increase by 5. Does that make sense? So the slope is giving you a kind of cost analysis benefit to studying, right? If I can get an extra hour study, I'll probably get about 5 more points, right? If I can get an extra 2 hours of studying, I should be able to get 10 more points up to a realistic limit. Now, what do you think the y-intercept is doing? If I wrote it down in mathematics, x? Wouldn't the y-intercept just be the place where it crosses the y-axis? But in the context of this story, what does that 30 represent? So how many hours would a student who's, well, I'm kind of giving the answer away there. I'll try and phrase it without giving the answer. What's the y-intercept score of 30 telling me? What kind of student is it telling me about?
They studied for 0 hours.
Right, so that would be what a student who didn't study got. Would that make sense? So the y-intercept tells us that a student who didn't study at all would get a score of 30. So do you see that the x and the y-intercepts, don't they tell you, the slope I should say, and the y-intercept, don't they tell you a little bit about what this situation is going on about, right? It gives you a little clue to the connection between x and y, right? So in this case, isn't studying a positive thing on your score, right? It has a positive influence on your score. What kind of influence? Well, for every extra hour, you get 5 more points. Well, what happens if I don't study? That's what the y-intercept will tell me. If I don't study at all, I get 30. Any questions about that? Because that's us for today. Right. I think we learned some cool stuff. Right. So say your last name and bye-bye, and I will see you tomorrow, where we'll continue working on this section, probably get it finished. That's my goal at least. And hi, Daniel, you got a question for me? No? Okay. Haley, Carson, any questions? Otherwise, I'm out of here. Haley, do you have a question? Okay, bye-bye.